In this video, we're going to discuss intermolecular forces, or what holds molecules together. You may have learned of bondings before with ionic, metallic, and covalent, what holds a molecule together. And in general, this is the positive and negative charges. Electrons are attracted to the nuclei. You can either distribute them through a metal in a sea of electrons, you can covalently share them between two atoms, or you can transfer them and create ions. Once that's done, however, the molecules then interact with other molecules. These are the intermolecular forces. What holds one completed molecule to another? And the truth is, it's the same, positives and negatives. But they play out in various ways. If we have ionic, this really holds up the same as it did at the molecular level. If I have a positive ion and a negative ion, they'll be attracted to each other and pull together. Well, if I have more positives and more negatives, this just continues. They'll stack to one another, they'll continue to attract, and you can grow your ionic material ad infinitum. There's not really a limit to the size of how big a salt crystal can be. This is an extremely powerful attractive force. While it can be pulled apart when we dissolve things, that's only because we get very good interactions with our next type, which is a dipole. When you made covalent bonds, sometimes you had bonds that were of fairly equivalent electronegativity. It might have been the same atoms, or it might have been fairly close atoms. However, if you ended up with atoms that were reasonably different, oxygen-hydrogen, carbon-oxygen, carbon-nitrogen, the halides, carbon-fluorine, and the electrons were shared, fairly equivalent things shared those electrons fairly uniformly. But when your electronegativities are reasonably different, the electrons skew towards one of the atoms. Their volume of their electron cloud is more polarized. It's more drifted towards one of the atoms. Well, as you transfer electrons off one atom to another, the one gaining it starts to look negative and the one losing it starts to look positive. As a result, when we haven't fully transferred, we get a polar bond, a somewhat negative and a somewhat positive. It's not like a sodium and a chloride where the electron would fully move and you'd get a sodium plus and an independent Cl minus. These are still sharing, it's just uneven sharing. Nonetheless, this is permanent. This is just part of the bond. As a result, there's a positive and a negative end to all of these bonds. Well, if you have two poles, a positive and negative, you have a dipole. This is a dipole bond, a polar covalent bond. Now, once you've made a molecule, say water, the net result is we have a lot more electron density up around that oxygen. They're skewed heavily off the hydrogen. So there's a big partially negative on that oxygen and some partially positives on those hydrogens. Well, since this is permanent, really we just have a molecule that generally has a negative side and a positive side. The magnitude of those charges aren't the same as the ions, but they're still just positives and negatives. And the same way our ions could line up, there's no reasons our waters can't line up. You'd have attractive forces between the oxygens and the hydrogens as the positives and the negatives are drawn to one another. This is a dipole-dipole interaction. Those residual charges from the covalent bonds forming can then interact with those residual charges on other molecules, either some of the same type of molecule or even just completely different molecules. In fact, in between these on the strength scale, you can have ionic dipole interactions. This would be when you have, say, a sodium ion and a water molecule. That partially negative on that oxygen can be attracted to that sodium. The hydrogens out here are still partially positive. In fact, if there's a chloride around, you can then have the hydrogens facing towards the chloride and being attracted to it. Well, this is a positive being attracted to a negative. Our negative oxygen is the same as it was for the other waters, but that positive sodium is a full positive charge. The greater the charges, the greater the attraction. This is part of why sodium salts are so soluble in water. There's a very good attraction between a fully positive sodium and a water's oxygen. And so ionic attractions are just full charges. Dipoles are partial charges due to covalent bonding of electronegatively different atoms. These dipoles can interact with each other. They can interact with ions. Ions can interact with ions. It's all these different types of interactions of different strengths. But they're all positives and negatives in the end. So what do we do about the ones that weren't dipoles? This is where our London forces or our van der Waal forces or our dispersion forces all come from. Really different names for the same general idea. This is what happens when you have things that aren't polar. These are non-polar interactions. When I've got a carbon molecule, let's say butane, it'll have hydrogens, and none of these bonds are polar. This means the electrons are fairly evenly spread out, and we can kind of imagine that on average, they just spread out more or less over the shape. Which means for any given molecule that doesn't have polar bonds, we have a generally uniform electron density. Simplified view, we'll have some protons in the middle, and we'll have some electrons around the outside. On average, these are pretty even everywhere, so there's no positive or negative difference from one side of the molecule to the other, like we saw with water. However, electrons are more fluid. We talk about the sea of electrons in metals, and we use formula very similar to fluid dynamics to measure electrons and their flow. They exist in a much more malleable state. So much so that if another molecule with electrons around it was to come bump into this molecule, it can force the other electrons to move a little bit. They push away from that negative charge, they get repelled and pushed over. And what can happen is, upon a small collision, you can, for a moment, unbalance this molecule. As a result, for just a fraction of a second, the bottom here is a little bit more negative, and the top is a little bit more positive. This will correct itself. Eventually that electron will move back up and this will go away. But for that instant, this is happening. Well, the next molecule nearby has its own electrons spread out. And as suddenly electrons show up above and the top half becomes more negative, these electrons get pushed away. And they drift a little bit away from it. In doing so, they expose their own protons, creating the top half here is more positive and the bottom is more negative. And now I have opposite charges that are adjacent to each other on opposite molecules. This results in temporary dipoles on a molecule. So it's still positive as negatives that are attracting these non-polar molecules. They just don't have permanent dipoles. Transitory, temporary, small dipoles emerge just from the collisions and the flow of the electrons around the molecule. For that instant that this exists, the molecules will get pulled together. Eventually, the electrons kind of flow back into position. The charges go away, and there's no net attractive force anymore pulling them towards each other. However, for that moment, they were. And so random drift might try to make them spread out, but the little attractive forces that show up pull them back together. As long as the drift isn't too fast, as long as the temperature isn't too high, then these will hold together. And this is how things like gasoline, many paint thinners and the like, this is how they hold together. In the end, the attractive forces between molecules are not really fundamentally different than what holds a molecule together, but how they play out, the distances and the strengths are. Sharing electrons for covalent bonds is much greater than an intermolecular attraction. The distances and the orbital overlaps are very, very different in how strongly electrons are attracted to what source. However, any attraction is still some attraction and can pull molecules together. The greater the strength of that attraction, the stronger the material is and the harder it is to pull apart, which we'll see in our next video as we talk about the phases of matter.